Chapter 3.4, Graphing Polynomial Functions. Okay, remember the shapes of our basic square and cubic graphs from the translation sections? Right, all of our quadratic functions graph made a parabola, and all of our cubic functions look like this. Well, it turns out that all even degree polynomials have this basic end behavior, right? Have this basic end behavior. And all odd degree polynomials have this basic end behavior. Okay, so in other words, a fourth degree polynomial will look something like this. Notice the basic end behavior is like a quadratic. A fifth degree polynomial will look something like this. A sixth degree polynomial, something like this. Okay. And one more. Let's do a basic seventh degree polynomial. Now, all we have to do is find out what's going on in the middle. And a cubic. Now, we only did the cubes that we could use translations on, but if we had, a cubic function like this, it turns out its shape would probably, the ends are still the same, but that middle bit may change. Okay, and we know that a polynomial of degree n has at most n minus 1 turning points. Turning points are these humps we call. Here this graph turns and goes down, then it turns and goes back up. This one turns and goes up, turns back down, turns back up. So an nth degree polynomial can have at most n minus 1 turning points, meaning a second degree polynomial can have at most 1 turning point, which is our parabola shape. Now notice the word at most, right? So a third degree polynomial can have at most 2 turning points, and here's 1, 2. A fourth degree polynomial can have at most 3 turning points. 1, 2, 3. But this is the most it can have. It can't look like this, but it turns out a fourth degree polynomial could look like this. It could just have 1 turning point. It can have at most 3 turning points though. A fifth degree can have at most 4 turning points. 1, 2, 3, 4. So it could never look like this. However, it could look like this. But a third degree cannot look like this. So how many turning points can a sixth degree have? Correct. 5. At most. 1, 2, 3, 4, 5. And a seventh degree can have at most 6. 1, 2, 3, 4, 5, 6. Okay. And this idea, like our cubic had, let me go back and put that original cubic shape that we had. We said we'd talk about that later. Remember how important it was? We said that we draw that flat spot in our graph of our cube. Okay, that's an effect of multiplicity. In other words, that's the shape of the graph for just x cubed. That means this point right here there are really three zero solutions. If x cubed equals 0, then x is 0, x is 0, x is 0. So the effective multiplicity makes a little flat place in your graph. If the multiplicity is even, then it does like this, right? It makes a little mini parabola there. It touches the axis, is a flat place, and goes back the way it came from. Touches the axis, makes a flat place, goes back the direction we came. If the multiplicity is odd, it'll come up, touch the axis, make a flat place, and then continue going in the same direction. So, in other words, even multiplicity will look like a little parabola at that 0. Odd multiplicity will look like a little cubic at that 0. These are important features of our graph, so we want to make sure that we have that feature represented anytime we have multiple zeros that's the same number. All right, so let's put that all together and see if we can graph some of these polynomial functions. Here's our steps, and here's our process. The first thing I want to do is pay attention to the degree of the polynomial, because that tells me its shape. This is a third degree polynomial and the leading coefficient is positive. If it was negative, it'd be flipped upside down, right? So I know it's going to have the basic end behavior of a cube. Okay? Now, once we know our shape, our basic shape, I just need some points to fit in so that I can draw that shape in. I always want x and y intercepts. So I'm going to find the x-intercept. That means let y be 0. So the first thing I'm going to try to do is factor this polynomial, but I notice it can't factor. So I can find my zeros with my p's and q's. P's are factors of 8. Q's are factors of 1 in this case, so these are my p over q's. I'm going to do my synthetic division. I'm going to check Descartes' rule, see if I get any help. It changed signs, so no help there. What if I plug in a negative x? That would be negative, that would be positive, so no help there. All right, make sure I don't have any missing terms. 3, 2, 1, 0, and they all are in descending order, so that I can do my synthetic division. I'm just going to start with 1. 1 times 1 is 1. 1 times 6 is 6. 1 times 8 is 8. Awesome! I found a 0. Right? So I know x equals 1 is a 0. In other words, that is the point 1, 0. And now this is a quadratic equation, which is x squared plus 6x plus 8 equals 0. So I can factor that and get my other two zeros. I have x plus 4, x plus 2 equals 0. So here's my other zeros. X equals -4 for the point -4, 0. And x equals -2 for the point -2, 0. Also, don't forget that means I now have this thing factored. Okay, so I now know that f of x is x minus 1, x plus 4, x plus 2. Okay, so I have a point here, 1, 0, -4, 0, and -2, 0. Before I go much further, and none of them have multiplicity, I want to make sure that this shape will go through those points, and it will. Perfect. Okay, I need my y-intercept. Y-intercept is when you let x be 0. So think about this. If x is 0, x is 0, x is 0, my y-intercept is always this point right here. So my y-intercept is the point 0, -8. All right, so my graph is going to go like this, like this, like this. Hey, I have everything I need except I just don't know if my graph goes like this or if it goes like this or somewhere in between. So an extra point I need, I already have an extra point in between these two intercepts, but now I need an extra point in between these two to see how high it goes at this point. So I'm simply going to plug in and let x be -3. Right? So f of -3, and it's easiest to plug in right here where it's factored. That's why I wanted to see that factored. -3 minus 1 is -4. -3 plus 4 is 1, and -3 plus 2 is -1. So that gives me a +4, meaning I also have the point -3, +4. Okay, I have enough information now because I know it's that shape and I know the points it goes through to draw my graph. I also want to be careful and not draw more than what I know, right? Don't draw too much more than what you know. In other words, I don't want to draw this way down here because I'm not sure how far over it goes. Just draw what you know and try to make it go through the actual points that I know. And I don't want to go too high. But there's a very good representation of this function. All right, let's try it again with this equation over here. On this equation over here, they've already got it all factored up for me. So I can tell that I've got a 0 at x equals 0, a 0 at x equals 3, and a 0 at x equals -1. Now don't forget, I need to know the shape of my graph. So this would be an x squared times an x cubed times an x. That's a 6-degree polynomial. Its basic shape is going to look like a parabola on the ends. It's just going to have some stuff happening in the middle, and I have to find out what. Now, if it's a 6-degree polynomial, I should have 6 zeros. And notice I only have 3. That's because some of them have multiplicity. There are actually 2 that are 0. So at 0, I'm going to have a little parabola shape. And there are 3 zeros that are 3. So at 3, I'm going to have a little cubic shape because an odd number of zeros looks like this. An even number of zeros looks like that. So let's plug in my zeros. X is 0. Oh, notice that also got my y-intercept. X is 3. And x is -1. Okay, so let's see if this shape will go through those points, but I got to remember what happens at 2 of the points. So if I start over here at 1, it's just going to go straight through 1. But at 0, it's got to touch and turn around and go back down. And then at 3, it's got to touch and make a flat place and keep going. Perfect. That end behavior is going to work. All I need to do now is pick some points in between here so I will know how far down it goes, right? How far down it goes. So first of all, let's pick the point 1/2. So f of -1/2 is plugging into my function, -1/2 squared, right? Negative 1/2 minus 3 cubed and negative 1/2 plus 1. So that's going to be positive 1/4. Okay, this is going to be negative 3 minus 1/2, that's negative 3 1/2. Negative 7/2. So cubing it, it's still going to stay negative. 7 cubed is 343. 2 cubed is 8. And then 1 minus 1/2 is 1/2. So I know it's going to be negative. Negative 343 over 8 times 4 is 32 times 2. 64. So I might need to know about what this number is. Okay, and if we come over here and try to do the division, let's try 5 in there. What do you think? 5 times 4 is 20. 5 times 6 is 32. Yeah, so it's a little more than 5. So a little more than 5, maybe minus 5 1/3. Okay, so that gives me the point negative 1/2, negative 5 1/3. Now, that seems odd to me that it's going that far down when they're this close together. So I'm going to check my math on this. I'm plugging in negative 1/2. I've got negative 1/2 squared, negative 1/2 minus 3 cubed, and negative 1/2 plus 1. So that is 1/4. Okay. Negative 3 1/2 is 7/2, and 7 cubed is 343, and is 8, and then 1 minus 8. All right, I don't see anything wrong with that. Okay, now I'm going to pick, ideally, I would like to do 1 1/2. Okay, but as long as I get close to the middle, it's not that important to be exactly in the middle, right? So I'm just going to choose 1 to make my math easier. So f of 1 is 1 squared times 1 minus 3 cubed times 1 plus 1, or 1 times negative 2 cubed is negative 8 times 2. So that's negative 16, giving me the point 1, negative 16. So I'm going to go over here and change my scale a bit. Let's change my scale to go by 2's, right? I'm going to do it up here to say this is 2, 4, 6, 8, and negative 6, negative 8, etc. Okay, so when I plot these points, negative 1/2, negative 5 1/3, 2, 4, 5 1/3, I'll be about right here. And then 1, negative 16, 8, 10, 12, 14, 16. And then just draw your shape in, not forgetting about your multiplicity, right? So at negative 1, it goes straight through. But at 0, it touches and returns. And then at 3, I gotta see that flat place there. So again, if I could draw a very good representation for this function. Okay, I guess that was it. Let me know if you have questions.